Modeling distributions of data, chapter 2.1. So take a second and read percentiles from pages 85 to 86. So what is a percentile? A percentile describes location in a distribution, like quartiles, not percent correct. Make sure when you are describing percentiles are in specific locations. So you would never say an observation is in the 90th percentile, but at the 90th percentile. All right, so let's do an example. The STEM plot shows the number of wins for each of the 30 Major League Baseball teams in a recent season. Calculate and interpret the percentiles for the Colorado Rockies, who had 92 wins, the New York Yankees, who had 103 wins, and the Cleveland Indians, who had 65 wins. First, how many pieces of data do we have? Well, we know that the STEM plot says we have 30 teams, so that means there's 30 pieces of data here. Second, count how many values less than the given amount. All right, this is going to be what you're going to put over your total. So the Colorado Rockies have 92 wins. So if we look at our stem and leaf plot, the values that are below 92, there are 24 of them. So 24 out of 30 gives us 0.8. So therefore, they are the 80th percentile. The New York Yankees have 103 wins. So we want to count how many values are below 103. That's 29. 29 out of 30 is 0.96666. And we want to make sure we round that up to 97. So it is the 97th percentile. Cleveland Indians have 65 wins. So notice how there are two values for 65. There's two 65s in our data. So we want to count what is below both of those values. So that's the 4, the 2, and the 9. So that's 3. So there are 3 values below those 2 scores or 2 wins. So 3 out of 30 gets us 0.1, which is the 10th percentile. All right, so if 2 observations have the same value, like they do for part C, they will be at the same percentile. You want to calculate the percent of the values in the distribution that are below both values. That's why for number C, we did 9, 2, and 4. Percentiles should be whole numbers, so round your answer to the nearest integer if you get a decimal. So like for B, we got 96, it was like 96 point something, something, something. So we rounded up to the 97th percentile. Take a second and read pages 86 through 88. Here's a cumulative relative frequency graph showing the distribution of points scored per game for the 486 NBA players in 2016 to 2017. So Pau Gasol scored 12.4 points per game. What percentile is he at? Interpret this value. So I'm going to look at my graph right here, and I'm going to look where it says points per game, and I'm going to kind of guesstimate where 12 is, and I'm going to come up and I'm going to see where that is about. So it's about the 75th percentile, all right? And the 75th percentile is also known as the third quartile. What is the 25th percentile for this distribution, and what is another name for this value? So if we look at where the 25th percent might be, and then we go down to points per game, it's about 8.75 or about 9, okay? It's also known as quartile 1. So think 75 goes with quartile 3, and 25 goes with quartile 1. Don't worry about making the frequency histogram. All right, here's a quick check your understanding. Mark received a score report detailing his performance on a statewide test. On the math section, Mark earned, that's an interesting spelling, Mark earned a raw score of 39, which placed him at the 68th percentile. This means that Mark did better than 39%, Mark did worse than 39%, Mark did better than 68, or Mark did worse than 68. If you did C, you are correct. He did better than about 68% of the students who took the test. All right, so now we have Z-scores. So read pages 89 through 91. How do you calculate and interpret a standardized Z-score? Do Z-scores have units? What sign of a standardized score tell you? So first of all, to calculate a Z-score, you're going to take the raw score, subtract the mean, and divide by the standard deviation. It will tell you how many deviations from the mean the raw score is. It is also known as a standardized score. A Z-score also doesn't have any units, and the sign of the standardized score tells you if the observation is above or below average. So take note, the Z-score is not measured in the same units as the variable. So you wouldn't say Jenny is 0.99 points above the average, but Jenny is 0.99 standard deviations above the average. So let's do an example. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller, relatively speaking? That is, relative to other kids of the same ages. Who is taller? According to the Centers for Disease Control and Prevention, the height of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4 centimeters. The mean height for 12-year-old males is 149 centimeters with a standard deviation of 9 centimeters. Now, both Macy and Brody are above average in height. Brody seems to be farther above Macy in absolute sense. However, if we're looking at a deviation from the mean, Macy's actually taller. This is where we use Z-scores to find out how many standard deviations away from the mean the observation is. So let's take a look at Macy and Brody. So notice how in the upper right-hand corner, I have my little formula for finding a Z-score. So I'm going to take my raw score, which is X, subtract my mean, and divide it by the standard deviation. I'm going to use the data that was given to me in this example. So we know that Macy's 100 centimeters tall. We know that the mean of 3-year-old females is 94.5. And we know that standard deviation is 4. So I'm going to plug those values into my equation here. And I get 1.375. So Macy is 1.375 standard deviations from the mean. With Brody, I'm going to do the exact same thing. And I get 1. Brody is 1 standard deviation away from the mean. So Macy has a higher standardized score than her brother. Let's do another example. The single-season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961, Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. In absolute sense, Barry Bonds has the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of batters, quality of pitchers, hardness of the baseball, dimensions of ballparks, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to other hitters during the same year. So we're going to calculate the standardized score for each player and compare. So notice how on this chart, I have their hitting record, the mean, and the standard deviation. So again, I'm going to use my Z-score formula to figure out how many standard deviations away from the mean they are. So notice how when I do this, Babe Ruth comes out on top. Although performances were all outstanding, Babe Ruth can still lay claim to being the single-season home run champ, relatively speaking. Negative Z-scores. So in 2001, Arizona Diamondback Mark Grace's home run total had a standardized score of Z equals negative 0.48. We're going to interpret this value and calculate the number of home runs he hit. So this means that Grace hit 0.48 standard deviations below the mean of 24.1 home runs in 2001. So this way, I'm going to solve for that mean score. So I have negative 0.48 equals our unknown minus our mean divided by our standard deviation. Solve for x, and you get about 15 home runs. What did you find from the dot plots? After completing the dot plot examples, this is what you should have found. When you add a constant to all values in a data set, the measures of center, being the mean and the median, and location, quartiles and percentiles, increase by that constant. Measure of spread or shape, will not change. When you multiply a constant to all values in a data set, measures of spread, center, and location are all multiplied by that constant. The shape will also not change. Transforming data. So read pages 92 through 97. In 2010, taxi cabs in New York City charged an initial fee of $2.50 plus $2 per mile. The distribution of distance for one businessman was skewed to the right with a mean of 4.8 miles with a standard deviation of 2.3 miles. So what are the mean and standard deviation of the cost of his cab rides in dollars? So if we have our fare to be the $2.50 plus 2 times the mile, then we're going to take our fare, subtract our $2.50, set it equal to 2 times the mile, and then we're going to solve for the mile. Now, we know that our mean is going to be 1545 minus 250 over 2. And our standard deviation, we have 1020 over 2. If he standardized each distance, what would the shape mean in standard deviation of the distribution? So the shape is going to be the shape of the z-score distance, and it's going to be the same as the original. The center, we're going to be subtracting all the values by 1545 and changing the means to 0, dividing all the values by 1020, but since 0 out of 1020 is 0, the mean is still 0. And then our spread, subtracting everything by 1545 does not affect the spread, but dividing every value by 1020 changes our standard deviation to 1. If you standardize a distribution, the set of z-scores has a mean of 0 and a standard deviation of 1. Also, don't worry about this question at the end.